In abstract algebra, the idea of an inverse element generalizes concepts of a negation in relation to addition, and a reciprocal in relation to multiplication. The intuition is of an element that can undo the effective combination with another given element, while the precise definition of an inverse element varies depending on the algebraic structure involved. These definitions coincide in a group. The word inverse is derived from Latin inversus, that means turned upside down, overturned. Formal definitions. In a unital magma, let be a set with a binary operation. If is an identity element of an, then is called a left inverse of an is called a right inversive. If an element is both a left inverse and a right inversive, then is called a two-sided inverse, or simply an inverse, of. An element with a two-sided inverse in is called invertible in. An element with an inverse element only on one side is left invertible, resp. right invertible. A unital magma in which all elements are invertible is called a loop. A loop whose binary operation satisfies the associative law is a group. Just like can have several left identities or several right identities, it is possible for an element to have several left inverses or several right inverses. It can even have several left inverses and several right inverses. If the operation is associative, then if an element has both a left inverse and a right inverse, they are equal. In other words, in a monoid every element has at most one inverse. In a monoid, the set of invertible elements is a group, called the group of units of, and denoted by or H1. A left invertible element is left cancellative, and analogously for right and two-sided. In a semigroup, the definition in the previous section generalizes the notion of inversing group relative to the notion of identity. It's also possible, albeit less obvious, to generalize the notion of an inverse by dropping the identity element but keeping associativity, i.e., in a semigroup. In a semigroup, an element X is called regular if there exists some element Z in S such that XZX equals X. Z is sometimes called a pseudo-inverse. An element Y is called an inverse of X if XYX equals X and Y equals YXY. Every regular element has at least one inverse. If X equals XZX, then it is easy to verify that Y equals ZXZ is an inverse of X as defined in this section. Another easy-to-prove fact: if Y is an inverse of X, then E equals XY and F equals YX are idempotents, that is E equals E and FF equals F. Thus, every pair of inverse elements gives rise to two idempotents, and X equals X, F equals X, Y equals F, Y equals Y, and E acts as a left identity on X, while F acts a right identity, and the left-right roles are reversed for Y. This simple observation can be generalized using Green's relations. Every idempotent E in an arbitrary semigroup is a left identity for E and right identity for L. An intuitive description of this fact is that every pair of mutually inverse elements produces a local left identity, and respectively, a local right identity. In a monoid, the notion of inverse as defined in the previous section is strictly narrower than the definition given in this section. Only elements in the green class H1 have an inverse from the unital magma perspective, whereas for any idempotent T, the elements of he have an inverse as defined in this section. Under this more general definition, inverses need not be unique in an arbitrary semigroup or monoid. If all elements are regular, then the semigroup is called regular, and every element has at least one inverse. If every element has exactly one inverse as defined in this section, then the semigroup is called an inverse semigroup. Finally, an inverse semigroup with only one idempotent is a group. An inverse semigroup may have an absorbing element 0 because 000 equals 0, whereas a group may not. Outside semigroup theory, a unique inverse as defined in this section is sometimes called a quasi-inverse. This is generally justified because in most applications associativity holds, which makes this notion a generalization of the left-right inverse relative to an identity. U semigroups. A natural generalization of the inverse semigroup is to define an unary operation degree such that degree equals A for all or in S. This endows S with a type 2(1) algebra. A semigroup endowed with such an operation is called a U semigroup. Although it may seem that a degree will be the inverse of A, this is not necessarily the case. In order to obtain interesting notion, the unary operation must somehow interact with the semigroup operation. Two classes of U semigroups have been studied. I semigroups, in which the interaction axiom is A degree A equals A. Asterisk semigroups, in which the interaction axiom is degree equals B degree A degree. Such an operation is called an involution, and typically denoted by a asterisk. Clearly a group is both an I semigroup and a asterisk semigroup. A class of semigroups important in semigroup theory are completely regular semigroups. These are I semigroups in which one additionally has a degree equals a degree A. In other words, every element has commuting pseudo-inverse a degree. There are few concrete examples of such semigroups, however. Most are completely simple semigroups. In contrast, a subclass of asterisk semigroups, the asterisk regular semigroups, yield one of best-known examples of a pseudo-inverse, the Moore-Penrose inverse. In this case, however, the involution or asterisk is not the pseudo-inverse. Rather, the pseudo-inverse of X is the unique element Y such that xyx equals X, yxy equals Y, asterisk equals XY, asterisk equals YX. Since asterisk regular semigroups generalize inverse semigroups, the unique element defined this way in a asterisk regular semigroup is called the generalized inverse or Penrose-Moore inverse. Rings and semi-rings examples. All examples in this section involve associative operators, thus we shall use the terms left-right inverse for the unital magma-based definition, and quasi-inverse for its more general version. Real numbers. Every real number has an additive inverse given by. Every non-zero real number has a multiplicative inverse given by. By contrast, 0 has no multiplicative inverse, but it has a unique quasi-inverse, 0 itself. Functions and partial functions. A function is the left inverse of a function, if and only if is the identity function on the domain of. The inverse of a function is often written, but this notation is sometimes ambiguous. Only bijections have two-sided inverses, but any function has a quasi-inverse, i.e., the full transformation monoid is regular. The monoid of partial functions is also regular, whereas the monoid of injective partial transformations is the prototypical inverse semigroup. Galois connections. The lower and upper adjoints in a Galois connection, L and G are quasi-inverses of each other, i.e., LGL equals L and GLG equals G, and one uniquely determines the other. They are not left or right inverses of each other, however. Matrices. A square matrix with entries in a field is invertible if and only if its determinant is different from 0. If the determinant of is 0, it is impossible for it to have a one-sided inverse. Therefore, a left inverse or right inverse implies the existence of the other one. See invertible matrix for more. More generally, a square matrix over a commutative ring is invertible if and only if its determinant is invertible in. Non-square matrices of full rank have several one-sided inverses, for we have a left inverse, for we have a right inverse. The left inverse can be used to determine the least norm solution of, which is also the least squares formula for regression and is given by no rank deficient matrix has any inverse. However, the Moore-Penrose pseudo-inverse exists for all matrices, and coincides with the left or right inverse when it exists. As an example of matrix inverses, consider. So, as m less than n, we have a right inverse. By components it is computed as the left inverse doesn't exist, because which is a singular matrix, and cannot be inverted.